All right, let's continue. Oh, this is not working. Wait. There we go. I want to say first of all that I'm a little behind on my email. If you sent me an email in the last week and I haven't gotten to it yet, if it's critical, please talk to me after class today so that I can take care of some business that you're waiting on. All right, so I'm behind on my email. So if you send me an email, I'm not ignoring you. I just haven't gotten to it yet. What do we need to do today? Lab 9? Okay. Quiz 3 is going to look like these labs. Let's see, that's November 28, right? So it'll look a lot like this. It'll be, I'll give you a function like that, and I say implement that function. It'll be vectors, arrays, and loops. And what's the other question?
No, if it was going to be like number 2 that you gave us a sample quiz that we can work on.
A sample?
The actual test that you gave us.
No, I'm not going to put a sample up there, but you don't actually need a sample. The sample would be the labs. I'll just ask you this question. In fact, many of these questions that are in these labs on vectors and arrays, these are questions that I took off of old quizzes. So these are the kind of questions I ask in those quizzes. Yeah.
If you want for Lab 9, I have an example for exercise 1 that works.
Lab 9, exercise 1. What's better, to go through the whole process of solving it together step at a time? For process? All right, let's hold off on that. If I run out of time at the end of the period, then we can maybe look at your stuff. All right. All right, so this is Lab 9, exercise 1. I'm going to start by copying just some main. Yeah, and just do this. Okay, here we go. Just get the. That's the first step, right? Let's get our. There it is. We've got the shell started here. Okay, that's running. And now in this exercise 1, you need to implement this function. Let's go ahead and look at that. And the function uses a vector, so we need to include the vector header. And at this point, let's test that. Okay, looks good. We've got the header. The purpose of that test is to make sure that we have, the header file included correctly and everything is declared. And in fact, we can go one more step. We don't even know what the problem is asking for. I mean, other than to implement something here. And we'll end up having test code that looks something like this. We'll have a vector. We'll call it v1. And we'll do things with v1. We'll build it up. We'll put it into a state that we're going to then that will give us a good test. So let's say we push back a 0, and then we end up calling the function, and maybe that'll be inside of an assert. So we're going to do assert contains And we're going to pass in the v1 here, and an integer k. We'll say 0. Actually, obviously, I mean, it looks like we want to know if k is in v or not. This is a perfect quiz question. All right, this might be it. I mean, this is not that hard to solve. I'm not going to give you I may give you one or two involved questions, but I'm going to try to give you questions on the quiz that are, straightforward to implement, that are not too difficult. But then I'll throw in a few very difficult ones as well, okay, but not too many. So this contains, actually, the compiler should have rejected this, but it didn't. So it's not really enforcing things well. Well, it's generating some kind of a default return. It's probably returning false. But let's go ahead and return true here. So this is a stub. So that when we call contains here, that this will in fact contains will, it doesn't matter what we pass into it, it's going to return true. So the assertion should be all right. Let's just see if that works. There we go. All tests passed. And if we were to break that, well, we're not going to. We'll do that later. Let's see. So we put a 0 in the vector and we test to see if it contains something. There's one test. Well, I probably don't need to read this. Write a function that called contains that finds an occurrence of an integer k in a vector v using binary search. And binary search assumes that the sequence of values. So on the quiz, I might ask a variation of this problem, which is easier to solve, which is don't use binary search. Just, I want to know if k is in v. Tell me true or false. So then you would just iterate through the elements and seeing if you find k. That would be a typical quiz question. This one here might represent one of the difficult questions that I ask, which will be when a 1 or 2 maybe. Binary search, by the way, what does that mean, binary search? Binary search is what you do when you look up a telephone number in a telephone book. Have you ever done that? I mean, you're the younger generation, so maybe you've never used a telephone book. Huh? Or dictionary. Well, even that. I mean, have you used it? I never use a dictionary. I never look up anything in a dictionary or telephone book. I use my computer or my cell phone, right? But in the old days, well, what's a good example of binary search that might happen now? See, that's it. Our tools are doing it for us, so we don't actually have to do a binary search. But in the old days, if you talk to your grandparents, ask them what a telephone book is. And if you have to look up someone's telephone number, what do? You open the book in the middle and say, well, I need the phone number for Gomez. Well, I open it in the middle and I'm looking at, Moreno. I say, well, is it in the right side half or is it in the left half? Well, it's in the left half because G comes before M. So then I'm going to split the left half into 2 halves, and then I decide whether it's before or after that. And then, so I keep halving the number of pages that I'm looking at until I get there. That's called binary search. And in the old days, humans used to have to do that more often than they do now. So what we want to do is automate. We want to write a program that does the binary search. So we have a vector, and it's got numbers in it, and they're in an ordered sequence. So it's like 1, 7, 11, a million, 3 million, 10 billion. The numbers are increasing, or they're non-decreasing. They're non-decreasing. What does that mean? That means they don't have to be increasing. So the vector 1, 2, 3, 3, 4, 5, right? That's not increasing because there's 2 3s in there. 1, 2, 3, 3. As soon as you get that second 3, it's not increasing anymore. It's just flat. It's going flat. Well, it's not increasing, but it's not decreasing. Oh, it's non-decreasing. Right? So the math majors use this all the time, right? This terminology. So the vector is the the numbers in the vector are non-decreasing. So they're either going up or they're staying the same. And there we go. So we have binary search. Did we do a version of this problem where it's not binary search? Did we do that already? I'm going to put that on the quiz. Okay. I'm going to say implement contains. Don't do it as a binary search. Do it as a regular search. In other words, the numbers aren't necessarily increasing or non-decreasing. They're in any order. You have to just search through it and decide if k is in the vector or not. If I can remember, I will put that on the quiz. Okay. I'm gonna try. Well, 10 may be too many. I don't know. It'll add up to 100, maybe 5. I'm not sure. I'll see when I make the quiz up. But I also may put this question, this specific question. This is a very important sort of algorithm to understand. It's called binary search, and it's not that tough to figure out. So maybe I'll put this on there as well. But I'll try to remember to put on a simple search where the vector doesn't have an order in it. All right, let's do another one here. 1, 2, 3. Let's see. That's 4. Let's do another vector. 2. And let's push some things on there. And we have a 0, maybe we have a 10, a 10 and 100 and a 1,000 and a 10,000. That's not a great example, but how if we do this? Make this a minus 20. Make this a 101, just to see if we can catch a problem there. And let's do a little more. Let's do let's put 2 100s in there. It's non-decreasing. It gets flat at a certain point. So this should fail. It doesn't contain a 0, and let's make that this should fail. Let's make that like a 30. So that should fail. Which it doesn't fail, right? Oh no, so it should be like this. This should not contain a 30. But it should contain a minus 20. And it should contain a 10. It should contain a 100, and it should contain a 101 and 10,000. All right, so these should now this will fail because we have a stub. We always return true right now. So that means this is going to return true. It's going to say, contains is going to say 30 is in there. Oh, it's not. So that'll be wrong. So this assertion, the true that's passed in, that's returned here will be negated. So the expression becomes false. Now assert, we're giving assert the expression false, or the value false. So the assert's going to say, assertion has failed. And it'll show us the line where it failed. Assertion not contains v230 failed. Okay. So we're in control here. We're getting our expected result at this point. Now let's think about implementing this thing. So there's a so we have the elements that are in order. If we do a simple linear search, it's inefficient. If the vector was large, then it takes a long time to complete the operation. And so we want to use binary search so that the algorithm runs faster. And imagine you've got a telephone book. You want to look up, you know, Zelda. And you start on page 1, and you look at every name on page 1, and go to page 2. You know, it's not an intelligent way to do it, right? So what we want to do is jump into the middle of the vector, and then decide is the number that we're looking for less than or greater than where we're at in the middle, and then we make another jump. So we need kind of like the jump point. Let's use I as the jump point. And the jump point is the middle. So where is the middle? Well, let's use, you know, v dot size. We'll use the size function and divide by 2. And then we'll see if it's in there. You know, if v of I is k, then we return true. Just to show a little bit, so if we, you know, if it's right in the middle, we got it. We return true. But if it's not in the middle, then, well, we got to look elsewhere. And how would that be? Well, if it's not in the middle, let's say, you know, is what we have, you know what, I'm going to do it like this. For me, it's just easier to look at and to think about. So maybe k is less than the middle, the thing that's in the middle. If k is less than the thing that's in the middle, I'm going to use my style here, put that on the next line. If the thing is less than the middle, then you know, we're going to try the middle of the left side, the middle of the first half. So how do we calculate this? In other words, going to reset I. So, you know, right, it's between, you know, 0 and where I is now. So basically we would just take I and divide by 2. Right? That's the middle of the left half. Else, and I'm just going to put a comment in here, that else what we have is we have the case that that k is bigger than v of I. We know that this is the case because it's in the first condition. We see that, you know, if this failed, we know that k is not v of I, and then if this fails, we know that k is not less than v of I also. That means k must be greater than v of I. In fact, what a good programmer does here is they actually put in an assertion that in fact k is greater than v of I, just to check our logic and make sure, you know, I mean, it looks obvious to us that k would be bigger than v of I, but it's obvious, but let's put the assertion in there anyway. So this is a typical use of assertions as you're coding, just to check your reasoning, because your reasoning will always fail in a medium-sized program or larger. Will always fail. And if you put enough assertions in there, you'll be able to debug very quickly, because you'll see where your reasoning, where something that you did in your reasoning process was wrong, and you thought it was right, but you put the assertion in there just to make sure, and then you fail the assertion. You know where to go. You know where in your reasoning you have made a mistake. Now, if k is bigger than v of I, then I is going to need to be like it's got to be in the middle. It's got to be between I and size. It's got to be it's going to be I plus V dot size divided by 2, right? We're going to take the average of I is now in the middle, and V dot size is like at the end, and we want to divide by 2 to get in between there. And then we want to try again, right? And now that we've put I into a new place, either we found it, or we put I into the middle of the first half, or we put I into the middle of the second half. Of course, this code isn't going to work. We're just drafting our solution here, and we need a loop, right? We're going to keep doing this over and over again. Here's the hard part: is turning this thing into a loop. So we're going to have some condition here. I don't know what it is yet. There's going to be some looping. And, we're going to be doing this process over and over again. So trying again is, of course, just part of the loop, right? So we're just going to take that out. Now, in the loop, it'll have to be conditioned on, I'm not sure what. We could do something like, let's do this, just for now, just sort of trying to get there. See, we return here, so it's not an infinite loop. If we find the value, we're going to, eventually return. So this is called an infinite loop here. I mean, it's infinite if we don't exit the loop. Right, so this could be an infinite loop. So that expression is always true. That means we're always going to loop. And we initialize I like this. In fact, there's lots of different ways we can progress here, but I can see that what we're going to need is something like bookends. Like we've got this, say we're in the library, we've got this long shelf of books. And we want to find, and the books are in order, and we want to find a book with such and such a number. Actually that's a good example because we still go to the library sometimes. And we have this long shelf of books, and we're going to look up, PQ29.3, whatever. So we go to the middle of the shelf, and we look at the book that's there and say, well, is it after this book or before it? And we'll say, okay, let's suppose it's after the book. So let's pull that book out a little bit, see? Just to say that, okay, we know it's not to the left of that book. We're just going to pull the book out and make a mark there. And now let's go into the middle of the right part of the right-hand side, okay? And then we're going to look at that book. We're going to pull it out a little bit. We're going to see, is that the book? No, it's not the book. It's to the left of that book. Okay, so we're going to pull that. Now we have 2 books pulled out. And we know that it's between those 2 books. So actually, we've got these bookends. We got, we're narrowing it down. We know it's to the right of the one on the left, and it's to the left of the one on the right. So let's do it like that. We're going to need an I and a J. We're a left and a right. So let's do something. I think what's going to be. Let's let I be the index of the item way on the left that we know it's after, and let's let J be the index of the item all the way on the right that we know is it's less than. And so this comment doesn't make sense anymore here. In fact, I'm going to set J, I'm just thinking, maybe I'm going to set J to 1 past the end. So that's what we're doing here. V dot size, remember if V is of size 2, that means there's slot 0 and slot 1. So if we let J be 2, then 2 is an invalid index. I don't know if this is going to work, but I'm just going to guess. Let's do the same with I. Let's set it as an invalid index. You know what? That's not going to work. I'm going to wait on that. Let's do it like this. Let's make I and J valid indices. See, now here We don't know if k is equal to v of I or k is equal to v of j. We don't know that. So maybe we need to test that before we even go into the, let me think about that. There's probably a better way to write this, but, well, let me wait on that one. And maybe the expression is going to look, while I is less than j, so I and j are going to be coming towards each other. I is going to get bigger, j is going to get smaller. So at this point in the algorithm, I k is going to be bigger than v of I, and k is going to be less than, that didn't work. K is going to be less than v of j. But we don't know that for sure yet. I mean, we could test it here. Let's do that. There's a better way of doing it, but let's just do it like this. So if k equals v of 0 or v of I, it's the same thing at this point. If k is equal to v of I, then we return true. We're done. If k equals v of j, or v of size minus 1, and then we're done. So now these assertions are true. We know k is bigger than v of I and k is less than v of j. So what we want to do here is we got to get the midpoint. We'll call it M. And it's going to be, well, it's the average of I and j, actually. Right? We can take the average of I and j. That gives us the point that's in between I and j. The value that's midway between I and j. Right? So if I was 2 and j were 4, well, the middle is going to be 3, right? So 2 plus 4 is 6 divided by 2, 3. Yeah, and that verifies. That checks. So I think we got that reasoning there. So M is the middle. And now we want to know is we've got M now. And let's say, well, did we hit it? Yeah. Well, return true. So M is the midpoint now. We're going to consider this midpoint. Let's return true. Well, okay, let's suppose it's not, k is not at this midpoint. In other words, it's either less than or greater than that midpoint. Let's suppose it's less than what's at that midpoint. If it's less than what's at that midpoint, then we're going to want to adjust I or j. So what we're going to do here, we know it's less than the thing that's in between I and j. So we're going to take j and slide it down to M. And we don't return anything yet because we want to keep looking. We reset j. Because we had 2 books pulled out on the bookshelf, and we pulled the one out in the middle between those 2 books, and we said, well, is the book we're looking for to the left of the middle or to the right of the middle? Well, it's to the left of the middle. Okay, I want to push in the book that's all the way to the right, and now call that mid book, we're going to call that the right end book, and then we're going to cut in half again. And I'm going to get rid of this comment. And the reason I'm going to get rid of that comment is because that comment is inside this assertion. So if k is neither equal to v of m or less than v of m, then it better be bigger than v of m. Otherwise, our reasoning is wrong. And if k is bigger than v of m, then it means that that we want to slide I forward. So it's in the right hand half of our split. Now the thing that at this point, I'm getting pretty comfortable that we got it right, but still there's the extreme points. What happens if, well, let's do this. What happens if we don't find it? Are we going to crash? Does the program crash? What happens if we don't find it? Well, if we don't find, at some point we're going to need to return false, right? We can't always just return true. We're not returning false anywhere in here. So what does this algorithm do if k is not in the vector? Well, let's analyze it. Let's analyze it with an example. Okay, let's take. In fact, let's code it up here as well. Well, here's an example that we have. It's a little bit large, but let's go with that. Here's the example. At this point, v is going to equal, minus 20, 10, 100, 100, 101, and 10,000. And this is a temporary comment. So we initialize, I is going to equal 0, and j is going to equal, what is it? 0, 1, 2, 3, 4, 5. So I is 0, and j is 5. That's the beginning of the algorithm. And so we look at v of I and k. K is say 30, which is right here. Okay. So we're going to do this. We're doing a walkthrough, a mental walkthrough on this problem. We've constructed v of 2. It's here. What is v of 2? We've constructed v of 2. It does not contain 30. We're going to pass a 30 in there. And let's just do a mental walkthrough to see what happens to the code that we just wrote. So the first thing that we're going to do is check to see, well, let's see, I is 0 and j is 5. So we're going to see if 30 is at v of 0 or v of 5. Okay, v of 0 is minus 20. Let me just put k in there. K is 30. So v of 0, v of I is minus 20. It doesn't equal k. And v of 5 is 10,000. It does not equal k either. So we passed the first part. Now we enter the loop. When we go into the loop, what do? It's, we calculate m. That's what we do. That's the first thing we do in the loop. We take I and j, we take their average, and we get an m. Is that what we did there? Do we take the average of I and j? Yeah, we did right here, see? We do I plus j, we divide by 2. That's the average. And so the average of, let's see, this is 0, 1, 2, 3, 4, 5. Okay, what's the average of 0 and 5? Yeah, question. No, we don't want m to be a double, and the reason is because m has to serve the role of an index. And the question is perfect, actually, because that's in fact what, just going to talk about this. You're right on the money there in terms of your question. the thing is, M, to be an index, it can't pass in, 3.5. It doesn't make any sense. It's not analog. It's a digital thing. It's discrete. There's a finite number of values. It's not a point on a line, in a continuous line where you can make the thing infinitely divisible. It's a discrete finite sequence of values and positions. So M has to be an integer. So what we do is, if we calculate 1.5, well, let's use 2 or 1, one or the other. Either one is good enough. We couldn't get exactly the middle book in the shelf. So, well, the one to the left or the one to the right is good enough. And when we do this division here, this is I and j are integers. So we're doing integer division. So we're going to truncate. We're not rounding, we're truncating. So here, m is going to be 0 plus 5, which is 5. 5 divided by 2. That's 2.5. But we're truncating. So m is 2. But, v of 2 is 100. It's right here. So we're going to compare v of 2 with k, which is 30. So 30 is less than 100. Let's look at the code up here. So m is 2. And so, we're comparing 30 with v of 2, which is 100. So 30 is not equal to 100. Is 30 less than 100? Yeah, 30 is less than 100. So j is set to m. J is set to 2. So we're going to slide j this way. And j becomes 2. Just going to tighten that up a little there. J now becomes 2. And we start the process all over again, right? So we do this, and then we go back up to this loop again, right? And then we check these assertions, and then we divide, then we calculate m again. I plus j over 2. I plus j over 2, that's 2 over 2, so now m is 2 divided by 2, so m becomes 1. And then we're going to compare, so that gives us 10. V of 1 is 10. So we're going to compare 30 to 10. Now, v of m, now k is bigger than v of m. So this happens. So now m, which is 1, is assigned to I. So we're bringing I up. You got to do this by yourself, by the way, to really get it. At this point, you're going to be losing it here, right? So, if you go through this process yourself mentally, then you'll get it. So this is, so now I is then pushed up to 1. And we continue the loop. Now, this is the point that we wanted to get to, right? So we got to figure out where are we going to return false. Maybe, we just do it down here. Because we have a condition up here. While as soon as I equals j, or I is bigger than j, if that's the case, then we're going to discontinue the loop and we're going to end up returning false. Is that sufficient? It's a guess. It's a hunch. But now we have to check it. So here we have I equaling 1, j equaling 2. Now we have to compute m. So we take 1 plus 2, which is 3, and divide by 2. That's 1.5. We truncate, we get 1. So m is 1. Oh, no change. M is 1. So m didn't change. Well, if m didn't change, then we're not going to we're going to do the same comparisons. We're going to do exactly the same comparisons, which means we come down to here. And we're going to set I to m, which we already did. So here we get an infinite loop. We never finish the loop. You know, that's a conjecture. It's an infinite. Let's see if we get an infinite loop. Whoops. Where is that line? It's a syntax error. We're going to fix that first. Line 23. Oh, I forgot to put the if in there. It should be else if. You don't have to worry about that on the quiz. But to get the program to run, you have to be, you know, in the lab you need to do that. Okay, that's that. So let's run it. I say it's an infinite loop and it never terminates. There it is. It's not terminating. So I had to kill it. Control C. So there's the issue when, you know, when we do this, if m becomes I or j, then that means, let's see how we're doing this. If m doesn't change, then we're finished. Let's see, if m doesn't change, how are we going to code that up? We could do, you know, if m is the same m, we're done. What's the other case? If after this, how about this condition? How about this? If I and j are 1 apart, while I is less than j minus 1. So in other words, you know, it's not good enough for I to be 1 less than j. It's got to be at least 2 less than j. Otherwise, there's no m to go to, right? If I were 7 and j were 8, where does m go? There's no place for m. So if let me do it a little differently. Maybe it's easy. Addition is easier to think about than subtraction. I have young children. I know that's a fact. Right? It's easier to think about addition. So if we need that I plus 1 is less than, is that more clear? That I plus 1 is less than j? Or we could do it like this. Maybe this one is more clear. If j minus I, the distance between j and I must be greater than 1. How about that condition? They must be separated by more than just 1. Well, my concern there is, you know, if the vector that's coming in only has 2 elements, we're okay because we're testing here, right? We're testing I will be 0, j will be 1. So we're going to test the 0 and the 1. And j will be 1, I will be 0, so that's 1, so this will fail, and then we end up returning false. So I think that's going to work. And we're running out of time here. I think we're going to pass all tests. We did. Now, you know, think about it. Searching for a book in a bookstore, in a library, this is what you do. This is what you do. The algorithm is not hard to understand because you do this algorithm. I don't know at what age do you comprehend binary search, but all of you do binary search. But is this easy to code? That's the thing. That's the hard thing. You know the algorithm, but how do you express it? How do you tell a machine to do what you're already doing? That's the hard part. And we probably need to do more test cases. Like here, this is Let's do a bunch of more test cases here. So V of 3. And let's not push back anything. So there should be, 10 should not, or 0, and that's a special case. We shouldn't find 0 in an empty vector. Do we want to allow empty vector? And also, we could expand this a little bit. We should test that it doesn't contain, minus 20. And it doesn't contain, say, like 2. Just the 0. Just expanding our test cases. I think this might fail, actually. What happens if V is empty? If V is empty, then I is going to be 0, and when we get to here, we're gonna look at V of 0, but V of 0 is not defined. So we have to test that. That is a special case. So if V dot size is 0, then whatever you tell me, whatever value k is, we know it's not in there. So I think I took care of that. There's a boundary. That's called a boundary case. I'm going to take this out too. The reasoning has been done. Let's test that. Whoop. 59. That failed. It's supposed to be V of 3. We're now, at this point, we're debugging the test code. We're not debugging the target code. There we go. All right, I think that was challenging. That's the beginning of thinking about how to get the machine to do what we know how to do easily. Yeah.
What's the segmentation fault?
Segmentation fault means you're trying to access illegal memory location. You're trying to access a memory location that the operating system hasn't granted you privileges to access. So it's a runtime error. So there's something wrong with your index. It's like V of minus 30. I mean, that's going to lead to a segmentation fault, I think, normally. A question?
Can you go back to the code, please? Are we supposed to call the function in line 8?
How do we call the function?
Like before the asserts, don't we call the function in there?
No. Because contains, the whole purpose of contains is, I'm going to give you a vector, V. I'm going to give you a number k, and you tell me true or false whether k is in there. That's all. So we're concerned about getting, what we're throwing in, and we want to make sure that what we're getting back is correct. So contains does not modify V1 here. It just reads V1. It looks at V1, tries to find 0 in there, and if it doesn't find it, it's going to return false. Or it returns true in this case because we put it in there. Yeah.
What happens if you put a number that's like you assert that like 10,001 doesn't exist?
So 10,000. So we throw in another assertion. So we can assert that that 10,001 is not in V2. Right? You want me to run it? You think it's going to crash, right? You're challenging the code here. That's great. That's exactly what you're supposed to do. No! Oh my God, you're right. What happened? You're right. The assertion failed. Oh, that's very good. Because this is this is bigger than the end element. That's excellent. Thank you very much for noticing that. We didn't pass in a value that was greater than the greatest value in the vector. And so the assertion that's failing is in line 17. Right there. So somehow K is not less than this. So there's another condition that we need in there. So when we calculate M, what happens? Let's think about it. We're going to have something like M, J is going to be, so we never increase J. So in this case, J stays the same. J is always 5. Say if we had 5 elements, 6 elements. If we have 6 elements in the vector, then it's 0 through 5. J is set to 5. And K is bigger than V of 5. Well, I know one way to do it, but maybe that's not the best way to do it. We could do it like this. If K is bigger than V of J, it's past the end. Let's get out of there. I want to tell you this, that what I'm writing right here is, if someone else looked at this, that does this all the time, they would say, this is terrible coding. I mean, we're just like thinking it out here. If you dwelled on this, you could make this very compact. But it wouldn't necessarily be, where we reason to. So we're reasoning to here right now. Marcus. Oh, thank you. We have to do the course evaluation today, so give me 30 seconds to finish this up. Thank you very much for bringing that to my attention. So I need to get out of here in just a minute. So if K is less than V of I, then we want to also return false. And let me put that one first. So this is the case where K is less than the first element in the vector. This is the case where K is larger than the largest element in the vector. And let's see if that fixes this particular problem. Thank you very much. That was an excellent observation that you had. That's fantastic. And that, in fact, fixes the problem. There's probably a more elegant way to do this algorithm. I'm sure of it. I mean, because I've done this before, and I know that there's a more compact way to express it. And we would have to spend more time looking at it to get to that more compact expression. So while you're waiting for me to pack up, let me shut this down.